start this problem by drawing a sketch of these three horizontal plates. So we're looking at it from above, that are put together to form the shape of an eye. We're supposed to find the total moment of inertia with respect to a vertical axis through the center, which would be represented by that dot. And we know the moment of inertia of each one of these because we're given the dimensions. They're all the same, width W and length L for every single one of these plates. So distance L up from there to there, and also this distance is W. This is going to be a parallel axis theorem problem to find the moment of inertia of each of these guys with respect to the central axis. I'll call this number 1 here. That's the easy one because we know the moment of inertia of it with respect to this axis, and this I'll let be number 2 and number 3. So our total moment of inertia with respect to this central axis O is going to be I1 plus I2 plus I3. Now I1 is just the moment of inertia with respect to the center of mass of any one of these. You know, the moment of inertia of 2 with respect to its center of mass would be that same expression. So I1 is just IC. I2, on the other hand, will be given by the parallel axis theorem. I think I'll go ahead and call that IC. It's going to be the moment of inertia with respect to its center of mass plus the distance that its center of mass is squared. So that'll be this distance right here. I'm working on number 2, so it's actually this distance. And I call that distance D. But it's the same as this distance. And it's going to be, let's say, this distance from the center out to one end is L over 2. And this distance is half the width of a plate, so that's W over 2. So this distance D is the sum of those, W over 2 plus L over 2, or I arbitrarily choose to write it in the other order, L over 2 plus W over 2. So this is that squared times the mass of one of these plates, and they've all got the same mass, m, so I'll just use the symbol m for that, plus m d squared. That'll be the second one, and then the third one plus, okay, it's got the same moment of inertia, and it's the same exact distance, so we get the exact same expression for it. So we've got, this all adds up to 3 times the moment of inertia of any one of them with respect to its center of mass, and we do have an expression for that up there, plus 2m d squared. Alright, let's go ahead and get that in terms of the givens. It's 3 times whatever our expression is up there, 1/12 m times L squared plus W squared in parentheses. and then plus 2m times d, that's this expression. I'll write that as one half of L plus W. And then this all has to be squared. So what do we get? 3/12 is 1/4. Then times m times L squared. I think I'll multiply that through. Plus 1/4 mw squared plus 2m times a half squared is a fourth, and times L plus W squared, that'll be L squared plus 2WL plus W squared. That's that whole thing squared. So we got an M everywhere. I think what I'll do is multiply this out, just simplify that piece. So for now I'll keep this the same. One half m, it's 1/2 m times each of these terms, so 1/2 m L squared plus 1/2 m times this, which will just be MWL plus 1/2 m times this. Now we can gather terms, simplify a little bit. This is 1/4 ml squared plus 1/2 ml squared. That's 2/4 ml squared. So I get 3/4 ml squared plus I got 1/4 mw squared and a half. So same kind of thing. 3/4 mw squared. That's these two terms. And then this is the only one left, MWL. I think I'll just leave it like that. We could factor out an M if you want. I think it looks pretty simple the way we've got it written. Units are consistent. Everyone is a mass times a length times a length. Here W times W, L times L. Here W times L. So we're dimensionally